Perfect. Okay, so welcome everyone. My name is Rasmus Bro from University of Copenhagen, and today we have Vagelis Papalexakis from almost Los Angeles, UC Riverside, and he's going to talk about some recent work they did on joint tensor alignment. So it's related to couple factorization, data fusion, multi-block methods, whatever you want to call that, but with a little twist. So I'm looking very much forward to that. So please, Vagelis.
Thank you so much, Rasmus. I'm really happy to be here at almost Los Angeles this morning or afternoon, depending on where you are. And what I'm going to talk about is this paper we presented earlier a couple of months ago at ICDM, which, as Rasmus said, has to do with coupled tensor factorization as we know it, but with a little twist that makes things a little more juicy and hopefully fun. And this is work that is led by my student Yunshu Wu, and with help from Uday and Zia. And they're all folks at UC Riverside. So first, let me just motivate what the problem and the general kind of framework we're kind of studying things is. And yes, so if you have questions, you can post them on the chat. So, and feel free to interrupt me if you need to ask something that will help you follow the rest of the talk, because I would not want to lose anybody. So perhaps I don't have to sell anyone on this call, on this webinar, on the utility and coolness of tensor decomposition, but just for us to be on all the same page, tensor decompositions, especially of the form that just give you a very simple rank decomposition of a tensor, are extremely useful and extremely prevalent in so many different fields, and Rasmus being one of the pioneers of that paradigm in chemometrics. And the beauty of those methods are their simplicity and their kind of applicability into multiple scenarios. So the scenario that I have here is let's say a multi-view graph, where you have different friends talking to each other, and then they use different means of communication that generate this third mode. And what's cool about this is each one of those rank 1 components we can now view as a substantial pattern in the data. And when we're talking about community detection and multi-view graphs, each one of those rank 1 tensors is essentially representing a community that gives us information about the different manifestations and the different kind of subtleties of the social relationship. So that's just as an application that we have been focusing on in the data mining field, for example. I'm not going to go into algorithmic details, but essentially one would have to basically fit this model in some norm, and there's tons of different ways of doing that. And again, Rasmus would be a better person to talk about this than me. But let's just say that this model is extremely useful. This is our basic tensor model we're going to be using throughout the talk. Now, the other concept that I want to sort of get everybody on the same page is the concept of coupling, right? So let's say we have now not just a single data set, but we have two data sets. Let's say one is recording the user video activity. Let's say this user watched this video on that day on YouTube. And let's say we have another data set that records who bought what and when on Amazon. So a certain user bought a certain product at a certain day on Amazon. And now in typical kind of coupling scenarios, we are motivated to kind of, as long as there is a one-to-one correspondence between the users here on the first data set and the second data set, to somehow enforce the decomposition that I showed you earlier to basically make those two data sets live in the same latent space, right? So if I just break those two data sets down into their CP decomposition, then essentially the factor that refers to the users have to be shared. And there's a lot of work there that again studies the extent to which those factors are shared, and so on and so forth. But in the simplest version possible, if I just make those two factors to be the same, then I am essentially making those data sets share this latent space. I'm jointly analyzing or jointly embedding in today's speak those two data sets in that low dimensional space. And the advantage of this is that I'm actually now able to identify common patterns and also use information from both data sets to fuse to each data set from one to the other, right? So if one data set has some missing data, maybe I can use the other one to compensate and so on and so forth. I'm calling it here couple matrix tensor factorization just because the CMTF as an acronym has been very popular. But in fact, here we have a couple tensor factorization, right? And so we can have matrices or tensors be coupled together, but a matrix trivially is a tensor. And so there you go, right? So in any case, this is kind of again, the simple framework that we can keep in mind when we're talking about coupled decomposition or coupled factorization. So now here's the twist, right? So as I said, the traditional way of looking at things assumes that there is one-to-one correspondence, or if there's partial correspondence, at least this correspondence is known. So I know that user 1 here corresponds to user A there, and 2 to B, 3 to C, and so on and so forth, right? And that's essential for me to be able to then make sure that I kind of forced the correct variables to be in the same space. Now, so what happens if this one-to-one or partial or whatever correspondence between those two data sets in the coupled mode is unknown? That's the twist that we're investigating, right? And if you come from a sort of a graph mining background, sort of first of all, what can we do? If we know, let's say that, well, those things are unaligned, but someone on the side gives us the alignment, then there's very recent work by Evrim, Jeremy, and Carla that essentially is doing what's called a linearly coupled matrix factorization. So essentially, you can see the same factorization as before, but now the two different factor matrices are related through a linear transformation. And if we knew, like, we can describe this permutation as a linear transformation. So if only we knew this, then we could just basically plug it in here and we're free to go. The problem is we don't really know that correspondence, right? And so if you're coming from a sort of a more graph mining background, you may recognize that this is a instance of a very popular problem, and especially in graph mining, people work on the so-called graph alignment or graph matching problem, where the setting is very similar. You have two graphs, and there is some correspondence across the nodes of the two graphs, but the correspondence is unknown. And your job is to essentially align the nodes, match the nodes, find the permutation between the nodes. And this is essentially the same, at the high level, essentially the same problem we're facing here, minus the fact that the two data sets we have can be something beyond a graph. It can be a tensor. It can have richer structure that perhaps we can exploit somehow. There is a lot of great work on that. We're not going to go into detail, but the first one that is now is got a darker color, Regal, is the method that we chose to use as our kind of go-to state-of-the-art graph alignment that we also use at some point as a baseline as well. And what happens is in all those methods, in general, there's two steps. The first step is to somehow go from a graph into a set of embeddings, basically node embeddings, factor matrices, if you will, for the nodes. They don't have to be calculated through a factorization. They can be calculated through a neural network, but there's basically n-dimensional representation for the nodes as a first step. And the distinct second step is to now find the permutation or some kind of probability of matching between them, right? So this is how this works in the graph matching space. And so if I were to kind of summarize why we cannot do this, what I just asked a couple of slides ago with existing tools is because, well, if we were to use linearly coupled factorization, we need to know the transformation beforehand. So someone needs to give us that alignment, and so we cannot do that. And if we were to use existing graph alignment techniques, we would first have to compute separate decompositions and then match them. And the problem is that this defeats the purpose of doing a couple decomposition in the first place, because we really want to put those data sets into some kind of common space. And so can we do everything basically all at once? This is the problem that we're going to try to solve here. So more formally, we're given two tensors, X and Y, and you can see here that, you know, they have certain slices that by color, you can tell that they match, but this matching is scrambled, right? And it's unknown to us. So given those two tensors, what we want to compute is their coupled decomposition into this joint latent space, A, B, C, D, E. A is shared. That's why we kind of have it on both sides, as well as this alignment matrix pi that is telling us how to shift things in order for X and Y to be perfectly corresponding, or, you know, because they obey a perfect model, A on either side to be perfectly aligned. And you may notice this pi here is essentially a permutation matrix. Is a matrix that tells us which rows are being permuted by which other rows. But this is the general problem definition. And we're going to try to solve this all at once, or at least formulate it all at once and then solve it in a certain way. So let's get right into the chase. Sorry, I was just checking at the chat. We came up with two different objective functions, two different loss functions, because we wanted to explore different ways of defining what we're trying to do. And we wanted to understand which one, if any, has a clear advantage, or whether, and more likely what ended up happening was that they have their pros and cons. So the first loss function is essentially perhaps what you would surmise from the previous plot. So what we have is, we're basically saying that X is going to be decomposed into A, B, and C, and Y, after permuting the rows of Y, is going to be decomposed into A, D, and E, right? That's the straightforward way of expressing the problem. And essentially, this is like the coupled CPD kind of sort of objective function after applying this transformation here. Now, a second way of looking at that is to kind of try to be a little more flexible. And so in the second loss function, what we're saying is, well, maybe we can actually do what I kind of said before we don't want to do, which is separately express that CPD of X, a CPD of Y, and then somehow make sure that alignment is obeyed with a different term. So in up here, alignment is obeyed by just directly permuting the data, whereas in the second objective function, we are enforcing it while also enforcing the coupling, right? Basically saying that the relation between the factor matrix for X and the factor matrix for Y they have to be really close after permuting for the rows. And the immediate modeling kind of advantage of L2 is that there are cases where, even though we wish to jointly decompose two data sets, they may not fully share the entire set of latent factors. And in this way, we're kind of allowing for this flexibility to have, you know, intersected spaces and kind of individual spaces at the same time. And we tested that with a data set provided by Rasmus and Evrim that I've worked in the distant past as well, but that's coming later. So those are the two loss functions, and we basically, you know, if you're familiar with tensor methods, the first thing one may want to try in order to solve a loss function of that form is to do alternating least squares, alternating optimization. And this is exactly what we went for, right? So basically what we do is, and this is just a skeleton for alternating least squares for this problem, is we'll just cycle over, we fix all but one variables, and we solve for the unfixed one, and we keep iterating until we basically converge to a solution. Okay, we have yeah, so Yazin, that's an excellent question. I'm going to talk about it in the very next slide, because indeed that's the part that is special here. So yeah, I'm just going to talk about that. So all the updates for ABCDE, as I said, are kind of standard, assuming everything else is is fixed. I mean, it requires some derivation, and the paper by Jeremy and Carla and Evrim is also similarly working on those problems. But what's new here is this pi here. And as I said, pi is a permutation matrix, has to be a permutation matrix, right? But if we try to solve for a permutation matrix exactly and optimally, we are into big trouble, because we will have to essentially consider something to the effect of all the different permutations, and this is going to be combinatorial. And this is a really bad thing for the scalability of the algorithm, right? Not necessarily only the speed, but also the size of the problem we can actually solve, right? And so what we ended up doing is something that is a little risky, but turns out it works well in practice. So I'm going to say what we're doing. I'm going to say then why it's risky, and then I'm going to show you results, right? So we really need to solve a approximate problem that closely mimics what this matrix would look like. And what do permutation matrices look like? Well, they are binary. They have row sum that is equal to 1. They have column sum that is equal to 1. So all those are constraints that we give to the linear least squares problem that we're solving. And they have to be orthogonal. And an additional constraint that we ended up using was because we wanted them to be very sparse. Essentially, if each row encodes a probability distribution of which row of one tensor is permuted to the other, we want this probability distribution to be 1 in one spot and 0 everywhere. And so essentially what we're saying is that the entropy of every row has to be essentially really small. We minimize the entropy, and minimizing the entropy means that essentially we are forcing every row to be just one spike, one position, kind of one hot encoding, because the minimum entropy here would be just a deterministic probability distribution, which is what we want in our case. All right. So this is essentially we're solving a linear least squares, constrained linear least squares problem where we are asking pi to obey all those constraints. Now, why is this risky? Well, it's risky for the following reason. When we're doing alternating optimization, the glue that keeps everything together is that every step has to be optimal, given that all the other variables are fixed. And we cannot really claim that we're solving optimally for pi, right? So we're kind of trying to sneak pi in and hoping that because it looks as close to the optimal, at least in terms of the constraints as possible, we can get away with it. In fact, we get away with it, but of course we observe that our convergence is not always monotonic as it would be if every step was optimal. But this is the catch here, and it was something that tortured us for a long time, because initially what we try to do here is we try to use any solver from graph matching, where basically we say, well, since we've reduced the problem into these are two sets of vectors, align them, why not use something like that? And the problem with all those methods is that they don't necessarily care about recovering the exact permutation. So what they do is they recover a probability distribution, and it's an actual probability distribution, not a trivial one somewhere. And the problem is that if we have such a really grossly suboptimal solution here, the whole thing just, does not converge, just goes somewhere to a very despicable place. And so that's why we really had to kind of think harder on what to do with this pi, and this is what we ended up with, and it works so far pretty well, albeit we'll keep trying to understand it and improve it. I don't know if this answered your question, Yasin, but this is basically what pi looks like. I'm gonna take it as a yes until asked otherwise. So let's move forward. So this is I'm not presenting the updates on the rest of the factor matrices. They're on the paper. I'm happy to send you the paper if you are not able to find it. But they're not, this is kind of what's more interesting and kind of more juicy here. So now, whoops, sorry. Let's go to see how this works, right? And how do you even start testing it, right? So we need to first set up how we evaluate the thing, how we go about knowing, you know, whether we're doing is right, and so on and so forth. So in the paper, we have tons of experiments, including sensitivity analyses and ablation studies. I've included some of it here, but I've mostly included the main kind of results, right? Because you know, sensitivity analysis is something that is also enjoyed offline with a cup of coffee or tea later. But I'm happy to talk about it after I'm done talking about the rest of the method. So in order to test it, we need data sets. And of course, you know, the first thing, at least I like doing when I start developing an algorithm, is make a fake synthetic data set that I have full control over, and I can understand when I'm messing up and how and why am I messing up. So this is what we started doing first. So we're building factors that obey the CPD model, right? And we are generating a linear transformation, basically a true permutation, and we're just making factors that we can just reconstruct to tensors, right? That will be, I think, you know, if you've worked on tensor methods before, I think that would be the first thing probably you would also do. And in this way, you actually know everything you need to compute, right? Of course, whether you're going to exactly recover those things, well, this is up to the algorithm. And if the algorithm is not giving you the optimal solution, then you may recover something close, right? But then this is the first kind of data sets we're looking into, synthetic, and we have different ways of generating them. And then we also have a real data set. Like, this is the one that I mentioned before from a paper many years ago now. We have with Evrim and Rasmus on essentially coupling, where we have joined and individual components, where I will probably butcher the motivation, but essentially, if you have different measurement techniques of chromatographic data, different machines are able to measure different subsets of the chemicals in the mix. And so chemicals equals components. If you have two measurement data sets, there may be an overlap of the things that both machines can measure, and there could be some individual components that only a given machine can measure, right? And so that's now to test whether our second formulation, which also allows for flexibility, is able to kind of do a better job at recovering those individual and shared components. So we get this data set, right? And we basically mess up one of the two tensors by directly applying the permutation on it, right? So this is, you know, essentially basically that picture here. Well, X is unchanged, and then Y is just permuted, right? And then we get to the setup where we want to, minus the part that now we don't really have the true factors, but we can hope that, let's say, if we applied state-of-the-art coupled tensor factorization on X and Y, those would be as close to the ideal factors, right? So we're using the state-of-the-art coupled factorization as our ground truth for the factors, because otherwise we don't have anything else to work with. So how do we measure goodness of solution, right? So there's two things we care about. We care about the alignment, and we care about the factors. So we want to measure things about both. For the alignment, we measure the accuracy, and the accuracy is essentially what you can think of as how many correctly aligned rows, or entities in general, we call them, divided by the number of entities, right? So if we have this scenario here, where basically the ground truth says that B goes to 4 and C goes to 3, but we said, oh, you know, A went to 3 and B went to 4, then here we would have those two would be the incorrect ones. So this would be subtracted from the numerator. Now, what we do on top of that is something that is inspired by the graph matching work, because of the way that those alignments are evaluated. And the observation is that at least in the graph domain, and essentially if we have a big tensor that would also carry, many nodes are essentially indistinguishable. And so in some sense, what happens is trying to exactly pinpoint which node exactly are you aligning may be a lost cause. And what happens is sometimes it's better to cluster your graph into supernodes and then align the supernodes. And so inspired by that, what we're doing is, in addition to the raw accuracy, which is referring to just edges, referring to rows of the data and full granularity, we're also clustering the rows of the tensor, and we're doing a clustering-based accuracy. So now, if we know that those two rows are in the same cluster, then if we had a mistake before that was going to the same cluster, now this is no longer a mistake, because we are following the same paradigm. Now, one may say, well, now you're making your life easier, you're making your algorithm look better, and indeed, this will actually sometimes be higher than the actual raw accuracy. But the claim here is that we're not doing anything that is more or less, embellished than all the state-of-the-art work in graph matching. And for good reason, because in many cases, you have rows of the tensor that are nearly indistinguishable. So trying to distinguish the minutiae may draw away from the larger picture. And so this is what we do for the permutation matrix. And we also have, we need to also measure the goodness of the factor matrices. And there we use a relatively well-established score, the factor matching score, that is being widely used in a lot of works. And I think this is the definition we straight up copied from Evrim and Jeremy's and Carla's paper. The idea is that essentially we have a ground truth factor matrix and the computed one, and we want, after resolving component permutations, because they can be permuted, the compositions are unique up to column permutations, right? So after resolving the permutations, we want to measure essentially the cosine similarity, the normalized inner product of those of the matching or the closest matching components. And if there is a perfect match, like in this case here, I mean, again, you can kind of visually see it. Believe me, those are kind of the perfect match. Or if it's an imperfect match, as is going to happen on the right side here, you're going to see that basically, the factor matching score is reflecting that. So 100% means perfect match. Lower than that means that there's some imperfections. There's some individuality in the factors that were learned, perhaps, or there's we just learned an entirely different set of factors if we're referring to something like that here. And so if we know the ground truth factor, then we aspire to be as close to 100%, right? So now, what do we test against, right? So this is the first method in tensors that does this, right? And so we don't really have an equivalent that is an apples to apples comparison, but we're trying to make as many apples to kind of apples comparisons as possible, trying to test different angles of the problem, right? So obviously we have two of our proposed methods with two different loss functions. And one thing we do is, as I said, we take the state-of-the-art graph matching subalgorithm, and we use it instead of ours. Now, one thing we observed by doing that is that is much faster, right? Can scale to higher scale problems, but the results are worse because it learns the probability distribution. It doesn't solve as hard of a problem as we have to. We are forced to solve a hard problem because we have to jointly kind of solve everything, but that's the takeaway here. And then we have a number of kind of different multi-step approaches. When I'm going to show you, I'm going to explain kind of step by step. The first one is kind of doing a two-step approach. First, decomposing X and Y separately, and then using the existing Regal kind of alignment method is aligning the separate components. This is not alternating, just two steps, right? And then the third one is essentially the same as before, separately X and Y, align using the graph matching algorithm, and then use the alignment in linearly coupled CMTF in order to compute the proper factors. So this is why we're doing these three steps. Well, the first two steps presumably only give us proper alignment. They don't give us proper factors because they live in different spaces. What if we now fed this alignment into something that would give us proper factors? And what would that be? Well, that would be LCMTF, right? That's why we have those three steps. And we're trying to see, okay, if we did those three things, would we get good alignment and good factors anyway, or do we really have to do this new algorithm, basically, right? Essentially, can we make do with existing tools or not? And so let's see what we have here. The TLDR is that, in fact, the proposed method, and not always one of the two loss functions, works better than those baselines that I had just described. And so the take-home message is that, yes, indeed, actually, treating those two problems, the alignment and the decomposition, in a joint manner is actually giving us a boost in both problems. One problem helps the other, right? Even though it's a harder problem to solve for pi, if we do it right, it actually, the end accuracy and the end factor matching score ends up being usually, for the most part, better, especially in the cases where we're using the joint approach. Now, let me show you more detailed results. What I'm showing here in each one of those those could be modern art plots, but they're not. They are actually joint probability distributions of the pi accuracy and the factor match score. If there were a single dimensional thing, if I was only showing you the pi accuracy, there would just be a histogram, right? And basically, good stuff happen on the top right corner, right? So basically, we want those probability distributions to have some high concentration as close to the top right corner as possible, right? Because that says we're doing really well on pi accuracy, we're doing really well on factor match score. Now, here you'll see those are different instances of either our method with different formulations or using Regal or doing the two-step approaches. Now, you can see that, for example, our proposed method up here has a tendency to be at least in the middle with a strong presence at the top right, compared to, let's say, methods like this where they have a really strong bias on one of the two variables, right? Meaning that they do very well, let's say, on factor matching score, but the pi accuracy actually suffers. And if you look at the 2 or 3-step approaches, they actually are not, they don't have a promising trend that tells us that there is something that can consistently give us a good answer. And so in that sense, it's a very hard problem, but the proposed method is actually able to do better than other things available to us, right? Not claiming that it does the best, obviously not, in solving the problem, because there's still a lot of room to improve. But this is a good start, and we're really interested in kind of developing it further. Another, just a small sensitivity result is with respect to the initialization. And so basically, we're looking into different ways of initializing the factors and the pi. Details are in the paper, but basically we're looking into whether we want to do CMTF first and then use those factors to initialize, or we want to give some kind of pi, that is well informed. Turns out that whatever initialization that we could think of we're using, we pretty much get a similar plot. Obviously, some of them are a little cleaner, maybe, but this is not to the degree of statistical significance that would tell us that you should only keep using one kind of initialization. So what this set of plots tells me is that all initializations sort of behave very similarly, which is at least telling us that the algorithm is insensitive to them. Now, whether that is good or bad, that's another story. But at least we know that we're not misrepresenting the algorithm by initializing it one way or the other. Now, in order to conclude, basically the message is simple. Doing factorization and alignment together seems to be better than doing things in separate steps. And basically the assumption is that this is because both subtasks are actually kind of synergistic and they help each other. There's a lot of work that needs to be done in the future. Primarily, what we suffer most with is scalability. And the reason is, well, even though we're simplifying the problem for pi, we're still solving a hard problem for pi because this constraint optimization is killing us. How can we scale to bigger size problems is something we're very actively working on and we're interested in. And then the other thing we're interested in is how can we extend it to different kinds of models, and what would that look like, and how would that be useful? With that, I'd like to thank all of you for your attention and thank obviously my co-authors without whom this paper would not be possible, and generous funding that also paid the bills and made everything possible. So thank you all so much, and I'm really happy to answer any remaining questions you may have.
Excellent. Thank you so much. And guys, if you have questions, just post them. But yeah, there's a question.
Oh yeah, there's a closed form solution for pi. No, this is a good question. We do not. We're doing a numerical optimization. Basically, we're solving, let's say, ax minus pi ay, subject to the set of constraints that I was presenting, right? So it's basically numerical constraint optimization. I don't know if we can come up, well, one could do the Lagrangian and then try to kind of put everything in a single formula, but it has not worked out so far, if that makes sense. Keshav is asking if the code, yes, the code is available for this. If you well, send me an email. If you cannot find the paper, like if you Google me, cannot find the paper where the link for the code is, please send me an email. I'm happy to send it to you.
Could pi be solved with linear programming or?
So essentially it is sort of linear it is just heavily constrained, right? That's the problem, and then that's why it's hard to scale to larger instances. Like it's the simplest thing we could do, right? But then maybe there's simpler or just faster things to do.
Right. So when you compare your approach to, let's say, warping and that kind of stuff, it's actually much more flexible, I guess, right?
So compared to what exactly you said? Sorry, I didn't
well,
catch.
correlation optimized warping and stuff like that, where you do an interpolation of a typically, whatever, a time axis or something. But you're actually more flexible because you can switch everything around kind of freely.
Yeah, and one can imagine, right? So we're interested in the permutation here, right? Because my motivation was from the graph matching literature. But if you're thinking of other kinds of linear transformations that may make sense, that would actually make things even easier, perhaps computationally, right? And could be like, yeah, this is not like, this is a more general framework that as long as you have a good solver for that linear transformation, then and in fact that I'm kind of solving alternating optimization at this point, right? But I think the way of thinking about it, if you have a different pi, that makes sense. That would fit right in.
There could be some Fourier-based stuff because some kinds of shift disappear.
Right. Oh, yeah. Exactly. Yeah, exactly. That would be, and then if you, so you can assume everything is in the frequency domain somehow, right?
Yeah.
This would work. Yeah.
Do you have any sort of opinion or intuition about uniqueness? let's say uniqueness of your method compared to no alignment, sort of.
Yeah, so only intuition.
Yeah.
But I feel that proper alignment should help with uniqueness. I mean, there's been discussions even on the converse, on like uniqueness of CPD is helping to recover better alignment, right? But I don't know if I have if I personally have the skills to show it, but I certainly like my intuition was always that. That's why I pursued it, right? Now, whether that ends up going to be true or not, it's unclear, but I think algorithmically we're still not there to study it because we're not solving it to the degree that we can kind of know, hey, this points to a unique kind of solution, right? But I intuitively, that was kind of all along my thinking that, at least I'm going to piggyback on CP's like Parfact's uniqueness to say those are the best embeddings you can use to align, right? And turns out that the converse somehow is happening because then I'm also getting better factor match score. So there is something there. It's just that I think requires a little more coffee and a little more, a little more discussions like this. Maybe you can come to almost Los Angeles, or I can come to exactly Copenhagen, and we can.
Yes. Yeah, that would be great. There's another question in the chat.
Let me check. Yeah. So if we try to compare with so yes, we did. So that's a good question. And this is, in fact, we first tried using exactly that, but we wanted to be more flexible. And let me go to the results here. The CPD plus Regal plus LCMTF, that's the, CPD and Regal gives us an alignment, right? And then LCMTF gives us essentially the factors. And you see, we have a good, like a big range of factor match score here. Now, I'm sure, although I don't think this ended up being on the paper, but I'm sure we used the alignment. I think if we use the perfect alignment, like the actual true alignment in LCMTF, we're getting a pretty decent answer for the factor match score, right? But that's not surprising. That's because essentially you're using the right transformation, right? So that's why we did not, I think we tried it, right? But we did not solve our problem. So this is not, I think, reported. But if we have an imperfect alignment, that's the problem, that if we have an imperfect alignment, because it's not changing during the algorithm of LCMTF, it's kind of propagating the error. You see what I'm saying? Whereas in our case, we wanted to disassociate all updates and change everything all the time so that we can move away from, let's say, some bad solution. Makes sense? Yeah. So, there was a question. How do you set the convergence criterion? Yeah, that's a good question. So I need to. We tried a lot of things, and I'm gonna now, like, I'm not. Let me remember. So one thing I want to say first is that the convergence here, if you look at the error, because of the fact that we're not really solving pi optimally, it's not going to be a smooth line, right? So it's a little more what you would expect from like a deep learning convergence plot, where you may see a little oscillation. And so I believe that we tried looking at a moving average and smoothing it out. And then when we see that the moving average doesn't change, then we call it quits. I believe that this is what we ended up doing, or what one should be doing. I do not recall what exactly is in the code right now. I need to check with Yunshu, my student, as well. But the added complexity is that because there's no monotonic, but there's some wiggly convergence, we needed to take care of that.
Another question: Did you try on matrix data?
I believe we did. We don't report it on the paper, but I think we did, because on the matrix data, essentially it would be as good as the constraint solver, right? So I would assume. I think we tried. It's just that I don't remember that being something that failed spectacularly, but also because it was not our goal, we didn't really kind of, this was more of a oh, we have a graph, let's just first try that on the graph. The problem is that we wanted to extend to kind of larger problems where usually those graphs live. And because we still cannot scale that well, we have not been able to get good results yet, right? So our first job now is to now make this thing scale.
Right, yeah, makes sense. But the reason I asked is that there's an old paper by Hashman who developed something called shifted factor analysis. You know, like it's well known that PCA or whatever bilinear model is not unique, but he hypothesized that if you add shifts, it's actually gonna be unique. He didn't prove it, but when he had an intuition, it was usually not far from correct. And so it's kind of, he had a very bad algorithm. So the method itself was never really interesting. But the idea that a two-way shifted bilinear model can actually be unique, and that's kind of related to what you're doing. Not exactly, but it's kind of.
Yeah, so, that's actually very interesting. I was not aware of that actually. I need to take a look at it.
Yeah, you should. It's Hong John. Oh, God damn it, I forgot his name. But it's Richard Hashman. 2 or 3 papers, shifted factor analysis.
I'll check it out. Yeah.
Yeah, it's actually nice. I'm not sure it actually relates to your problem, but it just seems to have a similar flavor.
Yeah, no, I think that's where the fun stuff comes from, right? When it's not immediately related, but it's the flavor of it.
Yeah, true. Another question.
Yeah, I guess you said so yeah, the scalability is currently on the tensor dimension, right? So on the number of variables we're trying to align, essentially. That's the bottleneck. The order, I mean, it couldn't, the order always gives you more, but this is predictable, right? So if we needed to align only on the rows, and then we just had a 5-order tensor, that would just be like the same hit you would get if you had a 5-order versus 3-order, right? If you had to align in multiple dimensions, that's a different problem now, because then, you know, you would have compounding errors potentially, right? We tried to align in follow-up work, we still follow-up and ongoing work, right? We try to align in both rows and columns, because let's say when you have a graph, like node to node, then it doesn't make sense to only align one side, right? You have to align both sides. And that seemed to scale the same way. But you know, currently the number of variables is the problem. And again, keep in mind, this is very beginning of the work, right? We were lucky that this was accepted at a very good conference. And so hopefully, you know, people saw its value, but still, you know, it has a long way to go. Thank you. Oh, thank you for the awesome. This is great.
Yeah, that's the paper. Never mind. Any other questions? I just have to say that this has a ton of applications, and I can't actually imagine all of them right now, but it's just obvious that this has a lot of applications. It's really neat. I like it a lot. So.
That was my hunch originally as well, and I'm glad that you like it. If you like anything in particular, or you want to talk more at some point, you know, where to find me. I'm in almost Los Angeles. So.
Yes, exactly. I know exactly where that is. Perfect. Any other questions? Otherwise, feel free to email, especially Vangelis, but you can also email me if you want, and I can send on any questions. And we will put the video of this on YouTube.
And let me put, just a second, let me put the PDF of the paper on the chat so that,
do that, yes.
You know,
and then I link it.
Don't have to be searching and, you know, agonizingly trying to find it.
Yeah, good. And I will also put a link to the second, no, never mind. The link to Hashman's paper is actually the link to his homepage, which is kept after his death, and you can find all his papers there. So if you just remove the last part of the URL, you have his homepage, I believe.
Right. Yeah, the page I know. I guess he had so many good works that I just.
Yeah, exactly. Yeah, everything he does is good. But yeah. Well, Vangelis, thank you so much.
Thank you. We have a message. Oh, thank you, Yasin. Thank you, Rasmus. Thank you, everyone. I'm really happy to have presented to you all. And again, the paper is on the link on the chat, and my name is pretty unique if you Google me. So happy to engage further.
Let me just save the link also. I will put it in the YouTube thing.
Awesome.
Perfect. Well, have a wonderful day.
Thank you so much. Have a great afternoon or evening, and bye from almost Los Angeles.
See you. Bye-bye.
See you later. Bye.
I will leave it open for I will, yeah, just leave it.